Okay, let's continue our discussion of op amps. So let's look at another circuit. This is called a differential amplifier. So this is something you've actually seen, sort of. You saw a differential amplifier when you used the Logger Pro in lab last week to compare or measure the voltage between 2 points. Okay, so this is the kind of how we can amplify some small difference between 2 points. So let's apply our cookbook to this differential amplifier. Is there feedback? Yes, the inverting input is connected to the output. We're assuming no currents into the inputs, V plus or V minus. We're going to find V plus. Well, if you look over here, what's connected to V plus, it's a little more complicated than what we've looked at before, but this is just a voltage divider. So we know how to find V plus. It's just going to be the ratio, or R2, over the total resistance times the input voltage VB. Okay, so we know what V plus is. We assume V minus is equal to V plus, was whatever our voltage divider gave us from the last part. We can, once we know V plus, or I mean V minus, we can find the change. We know the change in potential across R1, or this R1 right here, and we can find the current into the junction. So that's just delta Vn over Rn, but delta Vn is just VA, right? Because this is going to be on this side is going to be VA on the left side, and then on the right side is going to be what we calculated before, because V minus is equal to V plus is what we found from the voltage divider. So we get this complicated mess that we can write this way. Okay, fine. It's a complicated mess. That's the current. Once we know that, we can find the feedback current, right? Because the current into that junction is going to equal the current out of that junction, and nothing's going into the inverting input. So we know the feedback current. We can find the change in potential across the feedback. Well, if the IN was going into the junction, then the feedback's going to go out of the junction. The left side of this R2 is going to be plus. The right side's going to be lower potential. We can calculate the change in potential. It's just the current times RF. So it's our complicated current times R2, which is our feedback resistor. And then we can find V out, which is just going to be V minus, which we calculated up here, plus the change in potential, which we calculated here. And we can just write all that down. And it turns out if you do a bunch of algebra, do a few tricks, algebraic tricks, you get, at the end of the day, something that looks like minus R2 over R1, like our gain factor for an inverting amplifier, times the difference between input A and input B. So that's why this is a differential amplifier. So it amplifies the difference between the inputs VB and VA. Okay, so we can summarize that. V out's just going to be minus R2 over R1 times the difference between VA and VB. All right, I guess we're on to the next slide. So those are the basic circuits that we talk about: amplifiers, differential amplifiers, summers. Those are some of the basic uses for op amps. But it turns out when you actually go to use those op amps, there's certain limits, right? You don't get to, if you put in a 10-volt signal and your gain's 100, well, you may not be able to output 1,000 volts. And so there's some limits in what determines those limits. And there's really two ways to be limited. You can be limited in voltage or limited in current. Okay, so let's look at this. For a typical 741, which is what we're going to use in the lab, typically the maximum current that they can supply is 15 milliamps. And the limit on the output is V plus or minus the source voltage that you put into it. Now, typically there's an upper limit that you have to look up. It's on the order of 15 volts, typically. Okay, so let's look at the constant voltage source. So we have some op amp. We've wired it up as a non-inverting or an inverting amplifier. And so we look at that, we go, oh, well, the gain is going to be the ratio of the resistors. In this case, it's 1. So we put minus 1 volt in. We're going to get 1 volt out on the input. So now this is where we actually want to use it, right? Okay, we got 1 volt out. I'm going to put a variable load resistor out there, and I'm going to have 1 volt across it no matter what my resistance value is. So let's look at where the currents are. Well, what really is happening here is that there's some current flowing out of this source through the op-amp. A lot of the magic of the op-amp goes on, and then it sends out the current that comes out of the op-amp. Some of that current goes through the feedback, throws through the input resistor, and that's what sets up what's the output voltage going to be, right? That's our feedback. In this case, it's 1 milliamp. But it also is going to have to send out current to the load. If there's no load, it doesn't have to do this, but if there is load, there's going to be some load current that goes to the load resistor. So we can write that the current coming out of the op-amp is going to be the feedback current plus whatever current we send to the load. Well, if RL is infinite, then the load current is 0. So that's fine. The op-amp should be able to do that. But then as RL gets smaller and smaller, then IL gets larger and larger. And at some point, the load resistance, this is defined to be RL minimum, is when the current through the op-amp is going to be 15 milliamps. That's its limiting voltage. It can't supply more than 15 milliamps. It wasn't designed to do that. If you want more, you have to find some other op-amp that has a higher current maximum. But since we said, hey, we're current limiting the op-amp, right? Because we can't supply enough current. We can supply the 1 volt. That's fine. There's no problem putting the 1 volt out here. But if the load resistor gets too small, we can't supply that current. Okay, so typically a constant voltage source will current limit if the load resistor is too small. Okay, let's look at the other case where we have a constant current source. In this case, we're going to run the op-amp the same way, but now we're going to put our variable load resistor as the feedback resistor. So we're going to get a feedback current is 1 milliamp no matter what, because that's the current that's going to go through our input resistor. So we get this current, but as we change the load resistor, our change in potential across the feedback resistor is going to get bigger and bigger and bigger and bigger. And so you can imagine, right, if I'm going to have 1 milliamp and I make the load resistor something like 1,000, 10,000, and I get 10 volts. Well, that's fine, but what if it's higher than the 15 volts I'm putting on my on my op-amp? Then I won't be able to supply that voltage. And so to write that out, we know that the V op-amp, that's going to be our output voltage, or the op-amp voltage, is going to be V minus, the inverting input, plus whatever we change across the load. Well, V minus is, in this case, ground. It's whatever V plus is, and then we have the change in potential across the feedback current, which in this case is our load. Well, if the load is 0, then VL is equal to 0. Fine, but as you make RL, the load resistor, get larger and larger, then the change in potential gets larger and larger, and at some point RL is equal to RL max, right? That's when V op-amp equals the plus or minus source voltage that you've connected to your op-amp. So in this case, the constant current source tends to voltage limit, right? Because we pick some current that we know the op-amp can supply, right? 1 milliamp is with less than the maximum current it can supply, but it can't supply voltage bigger than the source voltage that we have hooked up to the op-amp.